Welcome everyone. How's it going? Doing okay? Okay. I brought, if you haven't picked up your first exam yet, I brought the whole pack. There's a couple people that emailed me and wanted them, so let me just bring them. So I do have them with me, so I get those to you. If you took a makeup, I think I've got them all graded, and I got those with me as well. So we'll take a look. Okay, tonight is kind of I kind of said this last time, but it's nothing too new. It's more an organizing way of taking a derivative, but we'll finish up chapter 11 tonight with 11.6. I did look through the scores, and a good number of you have not gotten into 11.3, 11.4, or 11.5, or one of the mix. So I have extended all of those till I think Sunday. I can't remember. I could do it again. But anyway, I just did it till Sunday. I think we're 26th. So those will be good to kind of finish up over the weekend. The main thing is those are the different ways of taking a derivative. What we're going to start getting into in chapter 12 is applications. So we won't be learning new techniques for taking the derivative. We'll be using these old ones. So that's the place where we're going to need you to have that practice of taking derivatives in the different ways. The product rule, the quotient rule, the chain rule. With, what did we do? We did exponentials and logarithms. Now, I also posted some additional things in the exponential and logarithms, some algebra for my algebra class, kind of review of exponentials and logarithms. I'm not sure that we end up doing a lot of algebra with the exponentials and logarithms, so you might not need all that, but it also might feel better if well, what does this function do, right? So there's some videos in there that just deal with the algebra of logarithms and exponentials. Okay. Tonight we're going to take a look at what we call implicit differentiation, and I'll show you. It's in a way it's nothing new, but it's expanding the tools that we do have to fit in to things that may actually not be functions. Well, no, they actually aren't functions, so I guess we'll put it that way. Any questions before we get in, or comments, or we doing okay? Just kind of do a check-in. We'll go over it. So basically, let me get in here. I've got some examples that we'll do. I put them in a Word document so I could have more space to work with them, but I'll just give the slide deck itself doesn't have a lot. It's just really a few slides. So let me go ahead and kind of use it a bit. We won't be here very long. But what an implicit function is a function that y is sort of an implicit function of x, and notice here we could actually get, we could have a y squared, we could get circles, we could get things that, again, we would say in algebra are not functions, and so we just didn't deal with them. This time we are going to find ways to deal with them, at least to get the derivative. Okay, so we can have these things where we don't really have an equation that is y equals something in x, right? Because that's really what we've been working with all along. But this is the one section we're going to take a look that we don't get y equals all this stuff in x. We've got maybe multiple y's, multiple x's, and yet the goal of all of this tonight is to solve for the derivative dy dx. Okay, and we're going to see that there's a technique that allows us to do it, and we've actually already been using it, but it just looks a little different when there's multiple y's in here. Okay, so again, you can kind of read through this, but basically you'll know it's an implicit function when there's a couple y's and you can't just solve for y equals. Then we're going to use this stuff. We're going to use this stuff again in chapter 12, I think next Thursday, when we get into related rates. Related rates there's two rates going on. So it's like a circle. the radius is growing at a certain rate, which means that the area of that circle, so there's an oil spill, we know how fast the radius is growing because how fast it's getting out there. We could then, the related rate is how fast is that area of the spill growing. We can do all of that with implicit derivatives. Okay, so we're going to focus a little bit on the technique and show you that really we've already been doing it. So this is something I think I invented. I mean, it might not be a great thing, so it's not that, I just haven't seen it before. But we're going to use this little technique here whenever, so basically we've got two variables. We'll have an x variable, a y variable. Whenever we take the derivative of a x variable, we're going to denote it as dx, and we'll read this as the derivative of x with respect to x. Okay, and when we use that word respect to x, that means that x is our input variable. So it's defining that. And what is dx over dx mathematically? Good, it's 1. Yes, it's anything divided by itself. We don't have to really know what they are, but anything divided by itself is 1. So we're going to see that we've kind of been doing this, but we haven't been writing it because it's just 1. But I'm going to use this technique because what we are going to be writing now, since we've got multiple y's, is we're going to use this little dy dx, and we're going to think of this every time we take a derivative that has a y, that is the derivative of y with respect to x. Okay, because so it's just telling us that we're favoring the x variable as the input, but we also have to deal with this y multiple times. Now, to show you that we've actually already been doing that, I want to just take maybe a straightforward one. So this is not necessarily an implicit, it's one that's solved for y equals 2x to the third plus 4x to the 7th. Just do that. When we took this derivative, we took the derivative of y and we just called it dy dx, right? Or just y prime. And we're going to do this, but we'll see that. Over on this side, we just took the derivative of x and we said, okay, the 3 comes down. 3 times 2 is 6. Subtract 1 from the exponent. That's going to be 2. And again, what I could do is I could say that this is the derivative of x with respect to x, but that's going to become 1. So that might be a little cumbersome to write, but I just letting us know that we've got basically, we're taking the derivative of all the variables, but we denote them differently. Okay, and then this last one, I have to take this derivative. 4 times 7, that's 28, isn't it? Sometimes I get these wrong because it's been a long day. And 7 minus 1 is 6. And that's a derivative of x with respect to x. And so we just wrote it as y prime, so we've done these kind of things, right? Okay. We're basically going to follow that same technique, and we're going to see that we can do the same thing, but we can do it with multiple y's and x's, and we're just going to follow this through. And then the harder part of this whole thing is once we've taken all the derivatives sort of independently, we may have some, we will have some algebra to do so that we get we will have multiple dy dx's. We got to get those together. The dx dx's, they're all 1 and they just disappear on us. So those are kind of nice. But so C web assign, which actually what I did is I went ahead and copied some of them I changed because I want you to be able to work through them. Let's see, I want to go back here. So I'll go to the examples, and I did it in a Word doc so I'd have enough room to work on things. And let's see, how do I is there a little, oh, here we go. We want to zoom. Let's make this bigger. Okay, I think this will all work. So notice we're just going to take this and we're given an equation and we're asked to find dy dx. And I'll kind of go through these and we'll make them, they'll sort of grow in levels of difficulties. So this is actually a fairly simple one. It's not solved y equals, right? So what we have to do though, I mean, you could do that, but then when you solve it for y, you'd have to take the square root and you get a plus or minus. You actually would get two different equations, okay? So you could kind of approach it that way, but this is going to be actually easier, as we'll say. So we're just coming here, okay, I've got three terms, right? I got this, I got this, I got this. We're just going to take the derivative of every term. So when I take the derivative of 5x squared, what do I get?
10x.
That's quick. Good. So yeah, the 2 comes down. 2 times 5 is 10. Subtract 1 from the exponent, so it's x to the first power. And what type of derivative did I take?
Oh.
I took the derivative of x with respect to x. Now, you're probably going to get tired of doing that real quick, but I wanted to do this. I am taking the derivative of everything, and this is a derivative of x with respect to x. Just remind you, when it's the important ones, we mark that when we got the derivative of y. Okay, so is that okay so far? Nothing really fancy. It's just this dx might seem a little strange, but it's just there for show. Then I'm going to take the derivative of 3y squared. Well, how do I take the derivative of 3y squared? Do the same thing. Bring the 2 down. 2 times 3 is 6, and it's negative, so we'll make it negative 6. Subtract 1 from the exponent. That's y to the first power. But what did I take the derivative of? Took the derivative of y with respect to x. So this is one that's really the important part. I have to put a dy dx there. See, that's what we're solving for. So you see then what's going to be left now is there's some algebra. Oh, I forgot about that 25. I have to take its derivative. Good, 0. It's a constant. We're not even going to bother that that's the derivative of it. It's not. It's just a constant, so its derivative is 0. But it's important to put that 0 there because people will say, they'll leave it blank like there's nothing there. 0 is actually something at least. It's at least a placeholder. So we got to put that there. Otherwise, we lose our equation, right? So now, what are we supposed to do? It just says find dy dx. There it is. I'm done, right? I found it. No. We got to solve for it. Okay. Bad joke. Okay. So what do? Get it by itself, right? So at the same time, let's say this dx, what is that? It's really just 1. So and we're multiplying by it. So it's kind of bothering me, right? It's in the way. So we'll just say it becomes just that. So what can I do now to get dy dx by itself? Subtract 10x from both sides, right? Just algebra stuff. So positive 10x minus 10x, that cancels. Negative 6y dy dx equals negative 10x. And now what do? Divide. So just algebra. Divide by 6y, negative 6y. Oh yeah, it's just algebra, but I remember Little Crow saying that's the hardest part of the calculus, right? It really is. So that cancels. So this is what our dy dx is. So we'll write it up here, dy dx. And I'll reduce this because 2 goes into both of these, so that's going to be 5/3. And the negative divided by the negative is positive. So 5x over 3y. We've got its derivative. Okay, so that's what we're doing now. A lot of your answers are going to have both an x and a y in there because of the process, right? It's going to be left over. And all we're doing is we're taking the derivative of everything as we go. And whenever we take a derivative of y, and I'm going to stop doing the dx thing next because it's kind of cumbersome. But every time I take a derivative of y, I have to put that dy dx. And you're going to see the next one we do, we'll actually end up with 2 dy dx's, and we've got to factor them out to make them just 1. Okay, so that's the next sort of big step. And then we'll get a little more, we'll get some x's and y's multiplied, and then we're going to have a product rule in there that we're going to be working through. But that's going to give us practice back on 11.3 was it? Or yeah, I think 11.3 was product rule. I've got some in here with exponentials. Give us some practice with 11.5. And you'll see that we're just doing the same thing, but now we've got x's and y's. But again, this is only one unit that we're going to do this in. And then we'll use it, we'll apply it in another application in the related rates. We don't do this a lot. Okay, so most of the other stuff will be just taking the derivative of x. Okay.
So,
Yes.
can you go to the first one, please? Why the 10x and 6y is divided by 2?
Just as a fraction, because 2 goes into 10 and 2 goes into 6. So it's just reducing the fraction. Is that? So you mean from here up to there?
Yes.
Yeah, so I'm just doing 10, 6. This is 5 times 2. 6 is 3 times 2. The 2's cancel. So it's just a reducing the fraction. Now you can always try in WebAssign. They might accept it. Sometimes they do. That's fine. Usually if they say simplify, they might mark that wrong. So sometimes you might have a right answer, but if it's not simplified, that's the problem. And again, the simplifying is the algebra part, and so it's oftentimes more taxing. Questions? But the process seem okay? Okay. So actually, I didn't, it's like going out there, we took a step into the little bit of the water, and now it's like a 10-foot drop off. So we're going to have 2 y's in here, so we're going to get 2 dy dx's. We're also going to have, what do you see happening here at the front? A variable times a variable, right? So we're going to have to use a product rule here. But we'll do it at the beginning because that's the hardest part. So we're going to do this, and we'll look at a little bit of practice, and we'll be all right. So product rule. This one's pretty straightforward. This one's pretty straightforward. Okay. Actually, I'll let you guys. Which one do you want to start? You want to start with the easier ones, or do you want to start with the? Let's start with the mess right from the start. Okay. Because if we get that done, then it's okay. So since it's kind of a mess, what we're going to do, I'm going to bring it over here. So that term, when we go to take this derivative, I want to see that this is, now the 3 is just a constant multiplier. So when we've got a number, you could just kind of, if you want, just say, let me take the derivative of this part, and I'll just multiply it by 3, right? Because that's what a constant multiplier does. Let's do that so that we don't get overly confused. So we really just need to take x squared times y squared. Oh, it's x cubed. And make sure you write everything down right, or else you get, thank you, that's cubed. That's my biggest problem is copying. Okay, so x cubed, y squared. But those are 2 different functions, right? What does the product rule say we do? You've got 2 things multiplied, f times g, right? Derivative of f times g unchanged, plus the derivative of g with f unchanged, right? So the derivative of the first one, x to the third, 2x, 3x squared, right? Okay. So the 3 comes down, and remember, we've got this other 3. We're just going to leave it up there. We'll bring it down at the end. So that comes from the exponent. This comes down, and then subtract 1. So we're going to get 3x squared, and I'm not going to put the dx, but we did take the derivative of x with respect to x, so that's okay. And then we have to multiply it by what? The second thing unchanged, so the y squared, it just tags along. Is that okay? So that's the first part of the product rule. Second part is we have this plus part here. Now we're going to take the derivative of the second function, which is y squared. Okay, when we take the derivative of the second function, what do we get? 2 comes down, subtract 1 from the exponent, we get 2y to the first power, right? So we just took its derivative. But what did we take the derivative of? We took the derivative of y with respect to x. So that we've got to put that marker. I just call it a marker. This is, oh, well, we're not quite done yet. Well, it just looks nicer. M times the derivative of the first function unchanged, so that's x to the third. And then remember to have our marker there, dy dx. Okay. So that's really the new thing, is we're taking the derivative of y, but we're marking and saying, hey, this is kind of a different, it's not just a regular derivative, it's a derivative of y with respect to x. It actually comes from the chain rule, but it's just, I just call it a marker. Every time you take derivative of y, put that little marker, this is the derivative of y with respect to x. Okay, we okay so far? And on all of this thing, this 3 has to come down, right? And it has to distribute to both terms. So I'm going to rewrite this over here. This little part here, its derivative is this big monstrosity. It's going to be 3 times 3 is going to be 9x squared y squared plus 6. And I'll switch the x and the y just because x cubed y to the first power dy dx. Okay. Yes, yeah, so I distributed the 3 here, so that gave me the 9. 3 times 2 gave me the 6. So I just kind of set it, strip it down to its bare bones, take its derivative, take the constant multiplier, multiply it through, so it's a little bit more consistent. And then this is the derivative of 3x cubed y squared. I might have to erase some of this, so we'll see. Okay, so now the easy stuff, or easier. What's the derivative of 6y to the 5th? 5 times 6 is 30. Good. Subtract 1 from the exponent, so it's now y to the 4th. But what did we take the derivative of? Took the derivative of y with respect to x. There is no x there, but it's a function with respect to x, so we have to put that dy dx. Okay. And even when my planning, I run out of room, so I'm going to, this is on video, so you'll be able to go back, but let's see if I can. And that's why it's always good to have all your eyes looking, because you catch all my mistakes before they become too bad, right? Okay, and then we've got our equal sign, and we've got to take the derivative of the stuff on the other side, right? So what's the derivative of 2x squared? 4x to the 1 power, right? The 2 comes down, subtract 1 from it. We don't have to put a marker because that's sort of x is kind of gives us that free. Okay, are we done? No. The goal is find dy dx, and we have 2 of them, right? We've got one here and one here. Okay, so we've got to get them to be one thing, and what's happening is they're being multiplied by a term, which is okay. So what we want to think of is we're going to use the algebra if I had 3x plus 3y, and this is just something I made up, right? So it's kind of a, maybe I should do something. Anyway, what could I do with these 3's? I could factor them out, right? And notice how I had 2 3's, but now they become 1 3. So I instead of factor, I say undistributed, because that's what, we take that 3, we're supposed to distribute it. So that's the same thing we're going to do with this dy dx, is we're going to undistribute it from that part. What I like to do first, though, is on this side, it makes a little bit more sense if I get rid of everything else that doesn't have a dy dx. So I've been red. So I'm going to subtract. So basically, I throw it to the other side. I'm going to subtract 9x squared y squared from both sides. Right. This becomes 0. and this now becomes 4 minus 9x squared y squared. We okay with that?
Want to see x squared?
Oh, it doesn't. You're supposed to have that there. I just, see, I tell you, it's been a long day, so my math is right. So thank you for watching and paying attention. I'm half asleep. Okay, so let me, good, so it's a 4 sec, okay. We got that. Now here's all the, we'll see the magic. So that what's left on this side, 6x to the third y. I'm going to change these into a different color. dy dx plus 30y, oops. Even when I say it doesn't mean I'm going to write it. 30y to the fourth. Because once you get, this is kind of the trickiest part of the whole thing. It's because it seems kind of unnatural. If I gave it to you to distribute it, no problem, that's the forward. But remember, this is sort of backwards, right? I'm undistributing. It's not a natural thing. We're taught to this, to get things simplified. So the move I do at this point is I take this dy dx and I factor it out, right? So I could put it in the front or I could put it in the back. I'll just move it to the back. And if I factor it out of those two terms, what's left? Well, 6x cubed y plus 30y to the fourth. And on this side, we didn't do anything, so it's still 4x minus 9x squared y squared. Okay, so that's, but this is the major step. We're going to factor it out, to undistribute it, and now what do we have? We have 1 dy dx, right? This is a major accomplishment. And how do we get the dy dx to be by itself? Because when they say find dy dx, they want dy dx equals stuff, right? What's left to do with this stuff in front? Divide it, because we're multiplying by it. So I like to just say, hey, it moves over and I just divide it. It becomes a new fraction over here, right? Let's go up a little bit. Like I said, no matter. So it's 6x cubed y plus 30 y to the fourth. And again, we divided that over here. So that cancels, and we just got our dy dx equals all that stuff. But you can see how it's so easy to make a mistake and a copy error here or there as you're going through that. But what you're going to do as you go through these, you're going to get practice with that product rule, because if we've got an x and a y together, we're going to have to use that product rule. You'll also get a little bit of practice with the algebra of moving things over to the other side. And you're going to have to figure out what's the best way for you to write everything out. How much space to give yourself. This was the hardest part of, I tell you, the hardest part I had going through math is I write up like maybe some of you, all over the page. My teacher taught me, try to keep it straight down and give yourself room, and that made a big difference. Okay. Make sure you're able to read your own writing. Sometimes I couldn't read my own writing. That was, So, and what is this? What did we end up with? What is dy dx? What is dy dx always? What is a derivative always? It's a rate of change. It's just a rate. Yeah. Okay. So it's not a value, it's a rate. It tells us how fast something's changing. And specifically, it's how fast, the change of y in respect to x. So as x changes, y is changing too. So that's what we're getting in these implicits. Both x and y are changing, but now we've got a way to kind of keep track of them both if we know how x is changing. And that's when we get to the related rate problems, what they do is they give us some values for x and y, and they might tell us how x is changing. We're able to figure out how y is changing, but that's the next step. Okay, we don't get there tonight. Tonight's just kind of like a skills-based thing. This is how we take that derivative. Okay, questions? That looks like fun. Okay, so where does this come from? Actually, we're going to have two product rules, right? Product rule here, product rule here. Fortunately, we don't have really too much of a chain rule to worry about, but we sort of do. And we've got an exponential, which we just learned about. This side is going to be the easiest because it's just got, something in terms of x. But again, we'll go through this. There's one very similar to this in the homework. The numbers are just a little different, but I tried not to change it too much. So as we go through this, you'll see it's actually helping with the homework. Okay. Well, let's just kind of go from left to right. So we've got x e to the y. So if you spell it out right, the first function is x. So what's the derivative of the first function? 1. The second function is e to the y. And so what's the derivative of the second function? It's e to the y with the marker, dy dx. But remember, e is its own derivative. This is it's simple, but it's confusing, right? So the derivative of e to the y is e to the y, but since we're taking, had this been we'll see it when we take it with respect to x, we don't get this marker, but since it's got a y variable, we have the marker. So we have to put that together, right? So this part here is going to become the derivative of the first part, which is 1. I'm going to write that down, times the second part unchanged, e to the y, plus the derivative of the second part, which is e to the y, dy dx. I'm going to put it this way, okay, because it tells us we took its derivative. But when you see e to the y and then e to the y, which one did we take the derivative? It's hard to tell. And then times the first one unchanged. So then there's times x. So that's the derivative of just that first x e to the y. Okay. Does it make sense? Feels uncomfortable though, right? It doesn't feel natural, but it's kind of what we're going to get you, practicing that product rule. And then we've got this one. Now this, I like to think of this negative sign as if it were a -1. So again, we could just kind of put it at the beginning. But I'm going to put this parentheses because since we have a product rule, right? Whenever times we have a product rule, we have a term plus a term. We got to make sure we distribute that negative sign through. Again, this is an area that's ripe for errors. And it's a small error. You don't distribute that through. You got one term that's off, but it's off. And the whole thing's off because of one little negative sign. Okay, so let's see if we can do this. So we've got y squared e to the x. So this time we're going to call the first function y squared. So what's the derivative of that first function? 2y to the first. Oh. This is where, what I've done is I put it down here, so I'm actually, So it's, figure out which works best for you. I find, I know I'm going to mess up that negative sign, so I'm going to write it down and then ignore it while I do the interim. But then that sometimes causes, dy dx, right? The second part of that is e to the x. And then what's the derivative of e to the x? E to the x. and we don't have any markers. So you see how this is, it's simple, but it's hard because you go, wait, really? But it is. E to the x is its own derivative. Okay, and now we got to put the pieces together. So the derivative of the first part, 2y dy dx, times the first part non-derivative, which is e to the x, plus derivative of the second part, which is e to the x, times the first part unchanged, y squared. Okay, and then now I would distribute my negative through. But again, maybe you could have had that in the beginning. And then on the other side of the equal sign, 3x to the fourth. 4 comes down, giving us 12. Subtract 1 from the exponent, giving us x to the third. We don't need any markers or anything. That's just kind of a regular derivative. So far, we good? Okay. So let me kind of clean this up. So we've got e to the y. I'm going to move this dy to the x of x. And then I'm going to put x's before the y's, x, e to the y, just to make it organized, sort of alphabetical order. And I'll change the dy dx to a different color. And I encourage you to do that or use a highlighter or something, because that's the part we're going to have to factor out or undistribute. I'm going to distribute this negative at the same time I clean things up. So this is going to be negative e to the x. Actually, I'll put the number. I'll put 2 e to the x y. So notice I'm taking this e and moving it in between the 2 and the y. So just ordering as numbers first, any variable with an x, and then any variable with a y, just to kind of help organize things. And then I've got this dy dx, which I'm going to do in a different color, because it helps me see what I have to get together. And then I'm going to take this -1 times this thing over here, so that plus becomes a minus, and it's already in good order, e to the x, y squared, and this is just fine, 12x to the third. So you see what we have to do? Anything that doesn't have a dy dx, we want to either add it or subtract it to get it to the other side, right? So let's go with green. So I see this first term, I'm going to subtract that just to get it out of there. And then this last term, I'm going to add it, e to the x, y squared, and it'll all come over here. So it's going to be minus e to the y plus e to the x, y squared. So this cancels out, this cancels out. We've got this place here. So let me move it up. Get that out of the way. Let's see. So then we're going to get on this side just x e to the y dy dx minus 2 e to the x y dy dx equals I'll just keep it that way, 12x to the third minus e to the y plus e to the x y squared. Okay, and again, order doesn't always make a big difference, but what we want to do is we want to solve for dy dx, so that we've got 2 of them. How do we make them into 1? We undistribute them. We put them in the back or the front, whichever way you want to go, but we take them out of those terms by factoring. And then inside, what's left? Switch colors. I guess we'll go to what's our last step? Divide, because we just divide by that whole thing. So we always end up with this fraction that has the stuff that didn't have the dy dx always ends up on top. Anything that did have a dy dx ends up in the bottom. So you'll see that that's kind of a pretty steady pattern. So it's just going to be this divided by but it's the derivatives of taking the derivatives when we have a product or anything else, you know, you see. So you might want a separate set of scratch paper to work things out, get it, and then bring it back over. But be careful if you're like me. My biggest problem is when I copy it back, I make the error. So, you know, just the main thing is kind of do what some of you could probably do a lot of this in your head, and you move forward, and that actually might be better for you. I start to lose things, and so, but find out what works best for you. Okay? Questions? Okay. Last one. Now, and there's about, I didn't count, but there's 3 or 4 problems at the end of the homework that are like this. They're going to ask you to take the implicit derivative. They're actually going to give you a point, x and y. And then they're going to want to know the equation of the tangent line. How do we get the equation of the tangent line? So let's talk about the last part first. What is an equation of a tangent line? It's got slope and it's got a y-intercept. So it's always y equals mx plus b. Where does the slope come from? That's a rate. It's the derivative. So really, once we're going to go through this, it's going to be, this is what dy dx becomes, right? The slope is dy dx times x. And we're going to have to figure out what the y-intercept is. Okay, so we could use the point slope form. I like to just use, I think, anyway, I like to just use this, plug it in, figure out what the y-intercept is. So we'll do that. And then, so we're going to find dy dx. Notice they give us a point that we're at, 1, 2. We're going to plug those in for y and x, which will give us a number, which is our slope. Okay, so once we find this dy dx, we plug everything in and we get some number. That's our slope. So we've got half our problem, and then we plug in that slope. We plug in the x and the y value, and we solve for b, and then we're done. Okay, so that's kind of our steps. But getting this dy dx is going to be the more challenging thing. So let's bring it over here. And notice I just copied and pasted this. When you go to do this, what will be different are the red numbers. So you might not have 4 or 12 or 2. The numbers will be different, but your equation is going to be just like this. So you'll be able to kind of use this as a template to follow through. And notice there is no product rule in here. There's some that do have it, so you'll get that practice. What time is it? Yeah, we'll have some time to take a look at it. But remember, after this, we really start focusing a lot on applications. So there's not going to be too much. We'll just be looking at examples and working things. So kind of keep your best going through that. So, okay, dy dx, what are we at? So we've got 4x squared plus 2y squared equals 12. Let's take its derivative term by term. So when you take the derivative of 4x squared, does that give us 8x to the 1 power, right? So we're okay with that. Take the derivative, and that's it. That's it. No product rule, nothing there. Take the derivative of 2y squared. 2 comes down. 4y to the first, and the marker. That's where the dy dx is. Derivative of 12, 0. Remember to put that 0. I'll see the papers that, oh, it's gone. It's nothing. It is something. It's 0. 0 is a number. Put it down. Now what do we do? Good. We got to get dy dx by itself, so let's get the stuff that doesn't have dy dx to the other side. So we get 4y dy dx equals negative 8x. And then what do? Divide by 4y. So we get dy dx equals negative 8x over 4y, which does reduce. 4 goes into 8 2 times. So you get negative 2x over y. Let's see, now what do they want? The expression of the slope of the tangent line in terms of x and y. So they want it in terms of x and y. So what we want to put in here is minus 2x over y. So that's what they want there. When we go to get the equation of the tangent line, they want it at the indicated point. So what does that mean? Plug in x and y in the derivative, and that's going to be our slope, right? So our slope down here, we'll just call it m down here, which is dy dx, is going to be negative 2. In this case, my x is 1. My y is 2. So that's 2x over y, right? That looks like it's going to give us negative 1. 2 divided by 2. So our slope is negative 1. I always like to write, we've got half of our equation ready to go. It's y equals negative 1x plus b. How do we find b? The way I like to do is I just take the point that I've got, I plug the x in for x and the y in for y, and then solve for b. So y is 2, right? Point 1, 2. Negative 1, x is 1. So 2 equals negative 1 plus b, so add 1 to both sides. It's like 2 plus 1 is 3, b equals 3. So what's our equation? Y equals minus x. That's how we can write negative 1 plus 3. Does that make sense?
Can you do it again?
What?
Can you do it again?
Do what again?
This one, the y minus 1x.
Sure. So when I add 1 to both sides, this goes away. 2 plus 1 is 3. Gives me that b equals 3. Actually, what I'll do is, how about if some of you might like this formula. There's, what is it? Y minus y1 equals m times x minus x1. I don't use, does that seem right? And then what you do is you plug the points in for y1 and x1. So that's y minus 2, right? Because the y is 2. The slope, we've got that is negative 1. And then x is 1. It should give us the same answer. So I distribute the negative 1. So that gives me a negative x, and a negative times a negative is positive 1. Add 2 to both sides. Can't go any further. And that gives us y equals negative x plus 3. Okay, so that's algebra. When we get to the tangent line, that's all algebra. The only part that's calculus is the slope comes from the derivative. So you remember that. That's all it gives us. And then the rest is just linear algebra. Y equals mx plus b, find that y-intercept. Does that help? but sometimes that's kind of the hardest, finding this thing. And the reason we do this is oftentimes, at least in a short frame, things behave very linearly. So what we've gotten is we do all this calculus stuff based upon data we've collected, but when we go into the future, that data may not hold. So what we want, if we get this tangent line, tangent lines will hold for a while, so we project off with the tangent line, oftentimes ends up being more accurate because other things are happening over here. And they're more simple. Computers can really, a linear equation is very simple to predict. Plug in x and you get y right away. The actual derivatives oftentimes are a little bit more complicated, and so we've got a derivative at a point, we can actually use it to predict what's going to happen tomorrow. We might not be able to tell you what's going to happen in 6 months, but the lines are pretty good at getting us to what's going to happen tomorrow. Sometimes. But just like the world around, all last week, the market's going up and up. What did it do today? It just tanked. But, there's no predicting that. But you can use it for its overall. And again, I was in financial. I still invest in stocks because overall, but you have to know when you can do that. You have to got to be willing to take a hit in a day, realizing that if you just stick in it for 10 years, it should be okay. Should be. That's always. And if not, we're all going to die anyway. So you can't take it with you. So don't fret too much. But you do the best you can. Okay. So those are the examples of basically every type that we have in the homework. So as you go working through the homework, you'll see these again. Kind of use these as sort of a template to go through. Practice. Remember 11.3, 11.4, 11.5, they're all open at least till Sunday. If you want some more time, just send me a message. I want you to get them done because that's how you're going to learn. And as you see, we start applying this stuff. If you're not proficient in the product rule, it really makes doing this stuff harder. And we're going to get into applications, and it's kind of going to be, but that'll give us some more practice. Got spring break coming up, so that gives us a little bit of time too. And like I said, I'm happy to open up things over that, take our test, and then after this test, what do we start doing? Integration, which is basically everything we've been doing backwards. So it's kind of, it sounds kind of crazy, but it's not so much new stuff. It's kind of just, okay, let's start at the end and go back to the beginning. So it'll help things sort of click. All right. That's all I got. If you hadn't picked up your tests and you want to, I've got them. I've got everybody's tests that hasn't picked them up. If you have picked it up, then you should have it.